Hello, welcome to the course on rocket mechanics principles. This is the first part of the course. Let's start with part 1, Origins of Rocks and Rock Masses. Part 1 includes 4 sessions. Session 1 gives an overview on rock mechanics, and its engineering applications. Session 2 covers the origin and the formation of different rocks and discusses rock textures. While Session 3 talks about the various geological discontinuities in the rock masses and the general features of the rock masses. The last session gives an overview on the surrounding conditions of the rocks, the in-situ stress, the groundwater, and the resources. We should start with Session 1. As an introduction, this session provides an overview on rock mechanics and its engineering applications. The course we're studying here is rock mechanics. So, what exactly is rock mechanics? All of you should have already studied mechanics at the colleges or universities, such as solid mechanics, fluid mechanics, structure mechanics, and soil mechanics. Then, what is rock mechanics? Obviously, we have the two main words, rock and mechanics. Therefore, clearly, the subject of study is rock, and the discipline of study is mechanics. In a more formal definition, rock mechanics is a theoretical and applied science of mechanical behavior of rock and rock masses. Defined by the U.S. Rock Mechanics Committee, rock mechanics is a branch of solid mechanics concerned with the response of rocks and rock masses to the force fields within the physical environment. The focus is mechanics, which deals with primarily force, deformation, and motion. I want to highlight to you that we consistently use the words rocks and rock masses. The mechanical behavior we want to study is of rock masses. Most people use the term rock to describe a piece of stone, and rock in general sense represents a stone block. However, in engineering, we deal with not a piece of rock, but a mass of rocks at the site, in the scale of engineering project. For example, when we excavate a tunnel of 6 meters in diameter, we are dealing with massive volumes of rocks, often adjointed, as seen from this rock surface in front of the tunnel boring machine. This large volume of jointed rocks at the site is the rock masses we generally refer to. In fact, for tunnel excavation we just mentioned, it will generate force and displacement to the surrounding rock masses within a volume a few times of the tunnel. For such a large volume, the rocks encountered are a massive volume of rocks. The classical solid mechanics we learned before are to describe a perfect solid. For example, a piece of metal. The materials are typically continuous, homogeneous, isotropic, and they behave linearly elastic. Most of the solid mechanics theory are based on those observations. And indeed, most of the solid we deal with as engineering materials are more or less continuous, homogeneous, isotropic, and linearly elastic. We often treat a piece of intact rock as a solid with the above characteristics. The rock mass, on the other hand, because it contains fractures and joints, as we see here, is definitely not continuous. The continuity is disrupted by those fractures and joints, and other forms of geological discontinuities. Rock masses at engineering scale have the characteristics and the mechanical behavior very different from a piece of rock. Rock masses are discontinuous, inhomogeneous, anisotropic, and non-linearly elastic. Rock mechanics have another special feature that is different from common mechanics, such as structural mechanics. In general solid mechanics, we usually define the load and then to estimate the deformation and the mechanical behavior of the material or the structure. In rock mechanics and in soil mechanics, we deal with the response of the rock and the soil when the existing stress conditions are disturbed by engineering. In another word, we deal with disturbed load. And the disturbed load is often not a known or a fixed load. They can be different due to the engineering activities. For example, the excavation sequence and the support method. Of course, the disturbed load is also very much governed by the existing stress condition that was in equilibrium before the disturbance and by the material characteristics. Rock mechanics has very wide applications to all engineering activities in counting rocks. The one you can immediately think of is mining, construction, patrolling, and hydropower. Mining engineering, particularly mining excavation, is very much a rock engineering activity. Typically, minerals are mined by surface excavation or underground excavation. It basically excavates the rocks and take the valuable minerals from the excavated rocks. And at the same time, to ensure the stability, the safety, and the environment of the mines. Mining are generally of very large scale. For example, very large surface mines can be up to 3.5 kilometers long, 1.5 kilometers wide, and 600 meters deep. Rock mechanics is the backbone of science and technology to mining engineering, enabling mining excavation to be done safely and environmentally. Application of rock mechanics in mining covers stability of surface mining slopes, excavation and support of access shafts and tunnels for underground mines, stability of underground mines, ground movements and subsidence, groundwater and gas outbursts in mines, and many more. In civil engineering, we use rock mechanics when we build any structures on and in rocks. Typically, they are foundations, slopes, and tunnels. Civil engineering structures are usually permanent structures and require good control in deformation. It hence requires good understanding of the response, particularly the deformation characteristics of the rock mass at the site. This is essentially rock mechanics. Application of rock mechanics in civil engineering include, for examples, stability and reinforcement of rock slopes, excavation and support of rock tunnels, design of building foundations in and on rocks, use of rock as construction materials. Oil and gas reservoirs are in rock formations, often deep below the surface. Extracting oil and gas requires the access through the rocks by creating wells, and more challengingly, by creating fractures in rocks. Again, we can easily name a number of applications of rock mechanics to petroleum engineering, such as stability of oil wells at great depths, creating of fracture network in tight rocks, movement and extracting of oil and gas through the rock fractures, enhanced oil recovery and replacement, possibly coupled with CO2 repository. Storage of oil gas in rock caverns, including LNG at a very low temperature of minus 180 degrees C. Hydropower generally is associated with dammed reservoirs and underground power generation plants. Hydropower systems usually are in rocky areas, and the dams mostly are built on and against competent rocks, while the power generation systems are often underground in rock caverns. It is again clear that hydropower engineering involves rocks and requires the input of rock mechanics, including design and the construction of dam foundations, stability of the reservoir slopes, rock tunnels and caverns for hydropower plants, particularly with large chambers and high internal water pressures. Geothermal energy from deep earth, a few kilometers below the ground, trapped in the hard rocks, is a potential energy source to be extracted. The hot rock geothermal energy is under exploration and development. Very soon, it will become one of the alternative, renewable, and green energies. But similar to other engineering activities in deep rocks, it requires comprehensive rock mechanics knowledge and technology to extract the heat energy, particularly to fracture rock mass to creating flow network. Other rock mechanics associated with this topic are seepage of water flow in fracture rock mass, heat transfer from rock to water flow, and sustainable balance of heat energy system. Earthquakes occur in rocks, often associated with sudden release of energy due to the movement of faults in rocks. The released seismic waves at the hypocenter travel through the rocks and eventually reach the Earth's surface to cause earthquake damages. Rock mechanics plays an important role in earthquake engineering in terms of understanding the natural and the induced earthquake initiation, seismic wave propagation in ground, and the effects of rock discontinuities on wave transmission, the effects of earthquake on engineering structures built on and in rocks. At the present, the solution for permanent radioactive waste repository is through underground storage in rock tunnels and caverns, either in granite or claystone. Both have extremely low permeability, preventing the movement of radiation. For good engineered radioactive waste repository in rocks, we need rock mechanics knowledge, such as groundwater flow in rock mass around the repository, long-term temperature, and the time effects. One of the possible CO2 sequestration solutions is the storage in deep geological formations, again in rocks. We cannot imagine to accomplish that without the knowledge of rock mechanics, particularly rock mechanics at great depths. One of the most ancient applications of rock mechanics is the fortification engineering, building protective structures in rocks to provide the best defense. So it will not come to a surprise to you that rock mechanics has great applications in protective engineering, such as underground shelters in rock caverns, design and construction of rock tunnels and caverns against explosion. I will end this session now. So far, we had an overview on why we learn rock mechanics. In the next session, we will start to learn about rocks. Goodbye, and see you later.